All right, so for the do not for today, all you were asked to do was to draw the dot structure for the elements of periods 2 through 3, right? So we pretty much cut off hydrogen and helium. Just to remind me, how do I draw a dot structure? Someone feel free to unmute and let me know. First of all, how do I know how many dots I need?
You have to go to the periodic table and then find your element, and then you have to look at the valence electrons, which is the last. You have to look at the outer shell, which would be the last number, and you basically just dot it, but you have to do it in like an organized way. You can't just like dot it anywhere. So your first dot would be like the slides the Ed Puzzle said, like dealing cards. So your first dot would be on top, then your next dot, depending how many valence electrons the element has. So you just like go in that order from top, the side, bottom, other side, and you just keep filling out until, yeah.
Thank you for giving us like a brief review, right? So this is what it looks like if we were to draw the dot structures for the first 2 periods. Just like Daniela said, when you look at the electron configuration that's at the bottom, you'll see 2-1, but remember that last number is the number of valence electrons, which is why we know lithium needs 1 dot versus beryllium, his configuration, if you're looking at the periodic tables, right, it's 2-2, which is why he has 2 dots. And then once you start having more than 1 dot, just like Daniela said, treat the element as if it has 4 sides, like kind of like a card table, right? So when you guys play Uno, you don't, some of us do this, but you're not supposed to. You're not supposed to just give each person 7 cards, right? You're supposed to go 1, 2, 3, 1, 2, 3, right? However many people you have. It's the same thing with the dot structure. So for example, beryllium, instead of writing BE and just say, oh, he has 2, put them on the same side, you're supposed to give each side a electron first before you start doubling up. So for example, carbon has 4, so it gets 1, 2, 3, 4. Then after you pass carbon, you'll start to see doubles, right? Because that way you have more than 4. So we did 1, 2, 3, 4, and then 5. And that's where we got. And then as you can see, dot structures look a little bit different, but there's also some similarities though. What similarities do you see and you should expect to see? Okay, feel free to put it in the chat or unmute. What similarities do you see?
Like when it's like the same kind of valence electrons, it's like Be and Mg are the same, and then E and Al.
Remember, that's because they're in the same group. So when we talked about groups and families, we knew that they had the same number of valence electrons. So since our dot structures are based on valence electrons, that explains why elements in the same group, pretty much their dot structures are going to look the exact same. The only difference is different symbols, clearly, because they're different elements. Cool. So what we're going to talk about today is something called the Octet Rule, which builds upon that idea of valence electrons and what they do. This is unit 5, and this unit is all about chemical bonds, the different types of bonds. There's actually more than one type. And how does this explain how atoms actually become stable? Because they're actually naturally unstable for the most part. First, let's look at some trends though. So based on what we talked about yesterday in the Ed puzzle that you guys had, atoms have mad electrons, right? So the dot structures only show the valence electrons. So why don't we include the kernel, aka the nucleus and the inside electrons when we draw these dot structures? Why don't we include that? So I want to give you guys some time to answer that question. Your responses. So let's look at some of these responses. First up, the valence electrons are the electrons that call chemical reactions. This person is not done, but you're right on the money. We don't include the inner electrons because they don't participate. They are too busy shielding and being super attracted to the nucleus. As far as the chemical activity or elements actually atoms interacting with nearby atoms of other elements, the same element, you have to have an electron that's free enough to go ahead and interact with somebody else, right? So that's why it would be too much to draw. That's another one too, right? Some elements, right, the biggest element has 118 electrons. Who has time to draw 118 dots? So if we were in person, Like, and we had a test. If I heard someone going like, you can automatically see that something's going wrong on that exam because that person is drawing entirely too many dots. You'll never need that many because we only care about the valence electrons. And then lastly, right here, because only the valence electrons contribute to the properties and the reactivity. So that's something we've actually talked about before in our previous unit when we were talking about the periodic table. Specifically, when we were talking about the different families and the different groups. So remember, I showed you the video of the alkali metals, how they all really don't like water, right? So the reaction gets worse as you go down the group, but that's one thing they all have in common. So if we go back and we look at their dot structures, we'll see that they all have one valence electron. So since they all have one valence electron, that explains why even still they all have a similar chemical and physical properties. So, and that the same can be said for most of the groups. Remember, it's not the truth for all of them, but for most of them. But the group we really care about today, Group 18, aka the noble gases. What's so special about them? What do you remember was characteristic of this family or group?
One thing I found that about the noble gases isn't that they had a full amount of electrons, like a full shell.
Don't they have this?
I heard full amounts of electrons. So you were trying to say?
Yeah.
Go ahead, keep going.
Don't they have
that
this?
was what I was saying. They had a full amount of electrons. They had a full shell of valence electrons.
And Sharon, what were you saying?
I was gonna say, don't they have the same valence electron, like the same last electron number?
Right, so I see that in the chat too. Somebody said, yeah, like they all have 8, right? For the most part. Right, aside from helium, who has 2. We're gonna talk about him in a few. But what's a specific property about the noble gases? Aren't reactive. Thank you, Joey. And the other word for that is inert, right? So they're called inert or non-reactive nonmetals. And that is because of the reason Ashton gave us, the reason that they have full valence shells. So since they have full valence shells, they don't need to react, right? That's why they're noble gases, they're bougie, and they're looking at the other elements like you wish you could be like me. And the other elements are like, yeah, which is why we react so that we can get like you, so that we can become stable. So noble gases are extremely stable to the point where that's why you don't find them in compounds, because elements form compounds to become stable, which is something we talked about when we were looking at the alkali metals, right? They don't like water. They're so unstable that we don't even find them outside of compounds, right? Because they have to bond with something else so that they can stop reacting with water and then they can sit down, right? And not be as reactive. It's all because they want to become stable. So when we're looking at dot structures, okay, so we know we don't need 118 dots. That's too much. But in general, what's the highest number of valence electrons an atom can have? What's the max?
8.
Right, 8, right? And you can see that when you look across the periodic table, right? We can ignore period 1 because that's an exception, clearly. But when we look at periods 2 and 3, we start off with 1 with lithium, 2, 3, 4, 5, 6. We get to the end with neon to 8. Then remember, it's called the periodic table because you have a repetitive or periodic repetition of chemical and physical properties. Here, it's a repetition of the number or the change in the number of valence electrons. Then when we come down to period 3, we go from 1 to 8. But we keep getting to 8, and the noble gases have 8, and that brings us to the entire point of this lesson, which is something called the Octet Rule. So the Octet Rule pretty much says elements bond, right? So elements that are not the noble gases, since they don't have to. All other elements, they undergo all these bonds and chemical reactions and stuff that we see because they're all unstable, but they're attempting to become stable by bonding with other atoms. So they bond because they're trying to get to, usually, remember that's in parentheses for a reason because there's always an exception, but they're usually trying to get to 8 valence electrons. So that's why it's called the Octet Rule. If you're taking geometry, you'll see octagon. Oct is the prefix for 8, so that's why it's called the octet rule, just as a way to remind you that most elements want 8 valence electrons to go ahead and give them a full outer shell. But that's not all elements. Let's go ahead and look at these exceptions. So when we look at elements atomic numbers 1 through 5, right? Couple things. If we look at their charges, remember, because we talked about this before, we can see if they gain or lose electrons, and we can also see their electron configurations. So my question to you is, why don't they need or want an octet if you think about what we've been talking about? So you have a hint here on the screen, which is what I was trying to show you guys a little bit earlier. And this, remember, is a picture of the Bohr model. So with the Bohr model, it shows how many electrons fit in each energy level. Now remember, this isn't the most up-to-date model in the sense that it's not 100% accurate, because things we haven't learned and will not learn because we don't have to in Regents chemistry is that there's levels inside the levels, blah. The one thing that is true though is that first energy level holds a max of 2 electrons. So remember, even though we call it the octet rule, you have to remember the reasons behind the rule, or the reasons why they want 8. And they want 8 because they want a full outer shell. So when we look at these elements here, all these elements are super small. So for example, for lithium, if he wanted to fill up level 2, remember every level 2 and up, they all want 8. Or he can just lose this 1 and just become 2, right? And 2 still counts as stable because that's a full outer shell. It's just the first shell. So that's something I saw in you guys' responses. So here they don't need an octet because they don't have room for 8 electrons. I know what you meant by they don't have room. They have room. They can still, it would be a lot of work, but they could still more electrons to fill up that second shell, but it's easier to just have that first shell full. So it's easier for them to just lose for the most part. And just like here, yeah, so make more sense to lose, right? So it's easier, right? Instead of stealing, you can just kick off what you have. So these smaller elements only need their first energy level full. So instead of something called the octet rule, you'll actually see this referred to as the duet rule. So remember, octet meant 2. Duet means, octet means 8, right? So that means it wanted 8 electrons versus, according to the duet rule, they only want 2. All right, so let's do some practice then. Then I'll show our responses because as you can see, we're all over the place, right? And that's a good thing because some of these statements are true. To fulfill the octet or the duet rule, which is something we just 8, but some of them can live with 2. Then second, have a full valence shell. Remember, that's where the octet and the duet come from. Either they want 8 or they want 2. Then lastly, create a stable electron configuration, which is what happens. That's what happens. They bond to become stable, and these are the reasons behind what makes them stable. In order to get an octet or a duet, right, so that should actually say octet and duet, we're gonna see atoms doing a few things. We're gonna either see atoms stealing electrons from other atoms. We're gonna see atoms being nice and donating electrons to other atoms, or we'll even see situations where neighboring atoms will share their electrons with other atoms in order to help both of them. It's a mutually beneficial relationship in that sense to make them all be able to attain either an octet or a duet and be able to become stable. And remember, everyone will do this except for our noble gases.